Alright, so today we are talking about similar triangles, and our I can statements for today are I can identify similar triangles using the angle-angle similarity postulate and the side-side-side and side-angle-side similarity theorems. We will also be able to use similar triangles to solve problems, both with and without algebra. Ooh, spooky. So, our first postulate is the angle-angle similarity. So, what this says is if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. And, of course, this is logical because we have, in triangles, if two of the angles are the same, then all three are the same. And if all three are the same, then the triangles must have proportional sides because all the angles are the same. So that's the angle-angle similarity postulate. Using this, we are supposed to determine whether the triangles are similar. If so, write a similarity statement. Explain your reasoning. So right off the bat, what I see is okay, we have two angles listed in each of these triangles. One of them is the same, one of them is congruent, and that would be angles B and D. However, the other two are not. But these are different angles in their relative position. So noticing this and knowing that they're in different positions, meaning that they're different angles. So what we would need to do is to calculate the third angle in at least one of these triangles. I would choose to do it in triangle ABC, mainly because I know 42 and 58. It's a round 100. Makes it nice and easy, which if those two are 100 when they're added together, then I know angle A has to be 80 degrees, which would leave me with two congruent angles in each of these. And so I would say, yes, they are similar. And that would be by the angle-angle postulate. What? Crazy. All right, so determine whether the triangles are similar. If so, write a similarity statement. Explain your reasoning. So right away, I pick up on we have two parallel lines, MN and QP, are parallel to each other. And then I see a couple of transversals we could use. So the first transversal I would like to use is MP. And using MP as a transversal, I know angle P and angle M here are going to be congruent. They're going to be the same angle measure, and the reasoning for that is alternate interior angles. So since they are alternate interior angles, we know that they are going to be congruent to each other. Now, continuing on, I'm going to use QN as a transversal also. And I'm going to see that angle Q and angle N are alternate interior angles as well, meaning that they must be congruent. So, since we have two congruent angles, two pairs of congruent angles across these triangles, then we know that they must be similar. Because if we have two pairs of congruent angles, we then, of course, have three pairs of congruent angles. So, similar, once again, angle-angle postulate. I'm guessing you're starting to see a theme here in these opening problems. A lot of angle-angle postulate. It's almost like it's the only thing we've talked about so far in this lesson. So, two angles are congruent across two triangles. They're similar. Triangles have to be similar. So, determine whether the triangles are similar. If so, write a similarity statement. Lovely. So that'd be 94. Yep. So these are similar. Reasoning being, this angle has to be 86 degrees because if we add 42 and 52, we get 94. 94 plus something is going to equal 180, and that something happens to be 86 degrees. So now the tricky part is we have to get these in the correct order, so I'm going from the 86 to 42 to 52. And I have to do that same thing for this other triangle. So ABC is going to be congruent to GFH. GFH. So that would be B. Yay. Continuing on, determine whether the triangles are similar. If so, write a similarity statement. So I'm not going to go through the whole reasoning again, but we do have two parallel lines, which means the alternate interior angles are going to be congruent. So I'm just going to go ahead and label those and hope that between this and chapter 4, we've kind of started to pick up on alternate interior angles and how much we love them. So now let's see. So they go from W, V to Z for theirs. So we're going to go W, V, Z in ours. So we go from the two line. So this would be our first one. Our second one would be V, and then our third one would be X. So what I'm doing when I'm labeling these is I'm trying to keep them in the same order to make my life easier. So they go W, V, Z. So 1, 2, 3, which means for our second triangle, we have to go 1, 2, 3 as well. So I'm going Y, V, X, which would be our first statement. So when I'm numbering those and labeling them, what I'm really doing is I'm just trying to save myself a little bit of time and trying to decipher exactly what these multiple choice options are. So I'm just trying to get them in the correct order. First try, quick, easy, painless. So next up we have our theorems. So we have side, side, side similarity theorem. And what that says is if the corresponding side lengths of two triangles are proportional, then the triangles are similar. So if side JK and MP are proportional, side QM and LJ are proportional, and side QP and LK are proportional, then the triangles are similar. So if all the sides are proportional, then they are proportional triangles, which makes them similar. Side angle side, what that says is if the lengths of two sides of one triangle are proportional to the lengths of two corresponding sides on another triangle, and the included angles are congruent, then the triangles are similar. So if we have a congruent angle like S and Y in this example, so if the sides on either side of that included angle are proportional, then we have a similar triangle. So it's very similar, using similar a lot, kind of annoying. So if words. So what we should recognize is that these theorems and postulates are very similar to the ones we went over in chapter 4, I believe 4.6, 4.7, 4.8, and they are true for congruent in that if they are the same, then the two triangles are congruent. Now we're using the same justification to prove that triangles are similar. The only difference is instead of the measurements having to be the same or congruent, now instead of saying congruent, we're saying proportional. So they have to be proportional to each other instead of congruent to each other. So this should all feel moderately familiar to you. So now we're determining whether the triangles are similar. If so, write a similarity statement. Explain your reasoning. Okay, so first things first, what I'm seeing we got three sides. So I know we're looking for side, side, side theorem, or side, side, side similarity theorem. That being said, I need to figure out which sides are corresponding to what. And just based on the pictures, what I'm seeing, I'm thinking, so let's just keep A, B, C. So we'll go 1, 2, 3. So I think this goes 1, 2, 3. So I think it's actually orientated the same, which would mean, of course, DC is similar to AC. EC is similar to BC, and then DE and AB are similar as well. So what I want to do is I want to check and see if there's a scale factor common amongst these. So I'm going to start off going between my 1s and 2s. So DE is 6, and then AB is 9. I'm going to set that up next to my 2-3 side. And when I say 2-3, I mean from my second point to my third point on each of these triangles. So I'm going to say 5 over 7.5. Then my final side, I'm going to go from my 1 to 3, meaning 4 over 6. So what I want to do next is I want to calculate my scale factor in these. And how I'm going to do that is I'm just going to reduce these and kind of see where they shake out. So first one, if I reduce this is 2/3. If I reduce 5 over 7.5, that's also 2/3, and 6 over 9 would also be 2/3, meaning that they have a common scale factor and that these sides are similar. So by side theorem, these are similar. Now I have to write my similarity statement. So this is where my 1, 2, 3's come in handy. So on this ABC triangle, I go 1 is A, 2 is B, 3 is C. And that triangle would be similar to, what is, oh, I'm so confused. So confused. Okay. Sorry. I started getting emails from some random family thing, and I have no clue what's going on with it. So, anyway, 1, 2, 3. So I went A, B, C, 1, 2, 3. Now I'm going to have to do that same thing on this second triangle. So I'm going to draw my triangle sign. I'm going to go 1, 2, 3. So D, E, C. Like I said, the order does matter on these, so that's why I try to label the vertexes and try to keep them in order that way. It just helps me. If you have a different way you like to do it, or if you just like to eyeball it, that's fine. But this is the most accurate way for me to get it done. Okay. So, determine whether the triangles are similar. If so, write a similarity statement. Now, there is a fun fact on these. Anytime you have a big triangle that has been cut into a smaller triangle using two of the same sides, then you have similar triangles. I forget exactly what that's called. I'm going to call it slasher theorem because it sounds awesome. But anytime you have a big triangle they have a line cutting it into a smaller triangle, then I should say anytime it's a line that's parallel to the initial side, then you have similar triangles. But anyway, if so, write a similarity statement. So I'm assuming these are similar triangles. So first things first, we have M, which is a shared angle. So that would be reflexive property. Angle M is congruent to angle M. So that being said, if these two sides, so if 10 and 25 are proportional to 12 and 28, meaning this whole length and this whole length, then we do have a congruent, or I'm sorry, we have similar triangles based on side angle side. That family email thing really threw me off. Now I'm just scatterbrained. So anyway, I'm going to set up a proportion to see if those are in fact proportional. So I'm going to do 25 over 10, set that equal to 28 over 12. So I'm doing big triangle side over little triangle side, and big triangle side over little triangle side. Now, I would cross multiply these. Let me rephrase that. I could do one of two things. I could cross multiply, or I could simplify. In this case, I can simplify this in my head, and so I'm going to do that. So I do 5 over 2. And then if I simplified this one, I would divide each of them by, did I do that right? Divide by 5, divide by 5, 5 over 2? Yeah, 2/5. So divide by 2, that should be 14. 14 over 6, which would be 7 over 3, which would not be the same. Ooh, boo. And they're not the same because I messed up in my addition. What? I thought so. Okay. So this side actually isn't 28, it's actually 30 because math is hard. So once I make that change, it should line up a little bit better. 30. Now when I reduce this, divide by 6, I'm left with my 5 over 2, which is lovely. So these are similar by side angle side. So once again, I figure out which order to put these in, and I'm going to start with M each time. So I'm going to go M, N, P, and I'm going to go M, R, S. So triangle M, N, P is similar to triangle M, R, S. Lovely. All right. Let's start grooving on these. So determine whether the triangles are similar. If so, choose the correct similarity statement and match the given data. So right away, these two angles are similar because they are vertical angle, or they're congruent because they are vertical angles. So congruent, they're vertical angles. Now we have to determine if the two sides are similar, and they are, because 2 times 3 is 6 and 4 times 3 is 12. Therefore, by side angle side, B. Continuing on, 2 times 2 times 2. Lovely. So A is the same as A by reflexive property. 4.5. Ooh, tricky. They almost got me. But not today. So I have to determine whether 10 over 15 is proportional to 9 over 13.5. They almost got me. So 9 times 15 is 135. 10 times 13, I'm sorry, 10.13, 10 times 13.5 is equal to 135 as well. Therefore, these are proportional. They are similar by side angle side. And more importantly, they are messing with us. So AFE, so that would be ABC. AFE, ABC, AFE. Yeah, A. Lovely. All right, so if RST and XYZ are two triangles such that RS over XY is 2/3, which of the following would be sufficient to prove that the triangles are similar? So if RS over RS over XY is 2/3, then we would need to know RT. We would need to know two other sides are proportional. Or the shared angle. That would work too. So RSXY. Angle R, angle S. That wouldn't do it for us. So I'm going to go with B. we are going to go with B because we would need to know all three sides, I believe. All right. So we have our properties of similarity. Feel free to jot these down. These are the same as the properties of congruence. Reflexive, symmetric, transitive. I don't want to say they should be second nature by now, but we should have a pretty good handle on what those are. Reflexive meaning that it's the same thing. Symmetric meaning that they just switch the order of the two things that we're comparing. And then transitive meaning if A is similar to B and B is similar to D, if A is similar to B, B is similar to C, then A is similar to C as well. All right. Continuing on. Now we get into some algebra, my favorite. So, given that RS and UT are parallel, RS is 4, UT is 10, and then these other two. Find RQ and QT. Delightful. So, first thing we would of course want to do is prove that these are similar, which we can assume they are based on these two angles being vertical, these angles being congruent as well based on alternate interior, and same with U and S being alternate interior. So we know the triangles are similar. Lovely. Now we can move on and say RS 4 over 10 is equal to x plus 3 over 2x plus 10. Go about doing a little solve. We get 8x plus 40 equals 10x plus 30. We're left with x equals 5. So when we plug this in, QT would be 20 and RQ would be 8. Lovely, lovely, lovely. All right, we'll do those together. Now we get into the interesting problem. So a big part of congruent or similar triangles is the real world problem solving, and you'll do more of this in trigonometry, but these are kind of fun. So using shadows, you can calculate very large lengths and distances that you wouldn't be able to calculate otherwise. So for example, in this problem, Josh wants to measure the height of the Sears Tower, the Willis Tower, if you will, in Chicago. He used a 12-foot light pole and measured its shadow at 1 p.m. So the length of the shadow was 2 feet. So we got this light pole here. It's got a 2-foot shadow. Now, he measured the length of the Sears Tower shadow, and it was 242 feet. So we need to figure out how high the Sears Tower is. So what we would say is a 12-foot object casts a 2-foot shadow, and a unknown height object casts a 242-foot shadow. And of course, the sun is in the relative same position, which means our angles are going to be the same, so we do have similar triangles. So we can cross multiply to find the missing length of this abnormally large object that we wouldn't be able to figure out otherwise. So we can cross multiply this up, or personally I would say let's reduce this so we have 6 to 1. We know this one's going to be 6 to 1, so we can multiply this bottom number by 6 and save ourselves some time. 242 times 6. So the height of the Sears Tower should be 1,452 feet. Now, let's do a quick little internet search and figure out if that's accurate, because I'm curious now. Sears Tower height. Ooh, so close. They have it listed at 1,450 feet. 1,729 if you count the antenna. All right, so you would solve this one on your own. So on her trip along the East Coast, Jenny stops to look at the tallest lighthouse in the U.S. So at the particular time, Jenny measures her shadow, and that shadow is 1 foot 6 inches in length. And the length of the shadow of the lighthouse is 53 feet 6 inches. Jenny knows her height is 5 foot 6 inches. What is the height of the lighthouse? So once again, we would do 5.5 feet over 1.5 feet equals unknown over 53.5 feet. So we would cross multiply this up. We'd do 5.5 times 53.5, and then we would divide that by 1.5, and we would find out that this tallest lighthouse is decimal madness 196 feet about. Alright, so here are some good visuals. I would copy these into your notes for the angle postulate, the side, and side angle side.